So in this very short tutorial, we're going to talk about double reciprocal plots, also called Lineweaver-Burk plots, based on the folks that came up with this approach. So the issue here is that the Michaelis-Menten plot results in a rectangular hyperbolic plot, so it's a nonlinear plot. So this is a curve. And before we had Excel or Kaleidograph or GraphPad or lots of these other graphing programs that could easily fit nonlinear data, this was problematic. And it caused significant errors in determining the value of the Michaelis constant, the Km and the Vmax values. So if you can take that nonlinear data and transform it into a linear plot, then you can make your life easier in terms of determining these. Now that doesn't necessarily mean that you limit the error completely. There are issues with this approach, but we can take the Michaelis-Menten equation, which we have here, and we can go through a relatively simple set of algebraic steps where we take the reciprocal of both sides. So we here we're just taking 1 over both the left and right hand sides of this equation, and then we're doing some rearranging. Okay, so take the reciprocal of both, we're just putting 1 over both of these values, then we just flip the denominator to the numerator to the denominator here. Okay, now we're just going to expand this out. And we get down through a couple of algebraic steps, and I don't want you to just look at these and say that's fine. I want you to actually work through these. Start with the Michaelis-Menten equation up here and go through these individual steps. It's very important that you be able to derive these simple linear transformations of the Michaelis-Menten equation. So again, we get down to this step, and what we want to do is take this form and rearrange it to a form that we're all more familiar with. Long ago and far away, you studied the equation for a linear line, y equals mx plus b. That should be plus, of course. That's not an equal sign. That should be a plus. Y equals mx plus b. So we want to put this equation, which we just carried down here, into that form. So 1 over the initial rate is our y. Our slope is Km over Vmax. Our x axis value here is 1 over the substrate concentration, and then our intercept on the y-axis is 1 over Vmax. Okay, so if we plot y versus x, 1 over the initial rate versus 1 over the substrate concentration, then our slope is Km over Vmax, our y-intercept is 1 over Vmax, and our x-intercept is minus 1 over Km. Okay, and this value is not given to you directly out of that equation. You have to actually solve for it. Okay, and again, this is something that you should make sure that you understand how you get this out of here. Okay, when we talk about enzyme inhibitors, I'm going to show you some plots for both the Michaelis-Menten equation and this Lineweaver-Burk. That way we can kill two birds with one stone. We can show the uncatalyzed reaction and or the enzyme catalyzed reaction in the presence or absence of inhibitors, in different kinds of inhibitors. Now, there are other linear transformations of the Michaelis-Menten equation. Okay, the Lineweaver-Burk is not the only one. E.D. Hofstee and Haynes-Wolff also did linear transformations, and they just did a little bit different representations, such that you're plotting different values of y and x. Okay, so again, you should look up the E.D. Hofstee and the Haynes-Wolff, and I don't expect you to memorize any of the Lineweaver-Burk, E.D. Hofstee, Haynes-Wolff, any of these linear transformations, but I want you to understand them to the level that if you're given the equation or asked to derive it, given the given the endpoint, asked to get from the Michaelis-Menten to that endpoint, or to be able to utilize the endpoint, then I want to make sure that you can do that. So we'll see some graphical representations in a subsequent tutorial.